Hello, I'm Pratibha S, working as Assistant Professor in the Department of Electronics and Communication Engineering of Government Engineering College, Ramnagar. I welcome to this video lecture series on the subject Digital Image Processing for the semester 7. I am here to explain the topic of smoothing spatial and sharpening spatial filters. This video lecture is a part of LMS under the Department of Collegiate and Technical Education. So for today's session 4, I'm going to brief topics like smoothing spatial filters, smoothing linear filters, order statistic filters, sharpening spatial filters. Under this foundation, using the second derivative of image sharpening, the Laplacian, unsharp masking, and high boost filtering, using first order derivatives for image sharpening, that is the gradient, are to be discussed. So let us see the topic. The first topic of our discussion is smoothing spatial filters. Smoothing filters are used for blurring and for noise reduction. Blurring is used in pre-processing tasks such as removal of small details from an image prior to object extraction and bridging of small gaps in lines or curves. Now, let us see about smoothing linear filters. Linear spatial filter is simply the average of the pixel contained in the neighborhood of the filter mask, whereas output is equal to average of the pixels contained in the neighborhood of the filter mask. Averaging filters or low-pass filters are used to reduce sharp transitions in intensities. The application of smoothing linear filters are noise reduction, smoothing of false contours, and blurring effect. So, the effects of the smoothing as a function of the filter size are illustrated in this figure, which shows an original image of size 500 by 500 pixels and the corresponding smoothed results. So all this figure B to B, C, E, A is the original figure, B, C, D, E, F, that is B to F are considered to be corresponding smoothed figure of the original image. So let us consider the square averaging filter of size M is equal to 3, 5, 9, 15 and 55 pixels respectively. So the principal features of these results are as follows. For M is equal to 3, we note a general slight blurring throughout the entire image. But as expected, details that of approximately the same size as the filter mask are affected considerably more. For example, the 3 by 3 and 5 by 5 black squares in the image are and the letter A and the fine grain noise. We can see here the fine grain noise show significant blurring when compared to the rest of the image. Note that the noise is less pronounced and the jagged borders of the characters were pleasingly smooth. The result for m is equal to 5 is somewhat similar with slight further increase in blurring. For m is equal to 9, we see considerably more blurring and the 20% black circles is not clearly as distinct from the background as in the previous three images, illustrating the blending effect. The results for m is equal to 15 and m is equal to 35 are extreme with respect to the sizes of the objects in the image. This type of aggressive blurring generally is used to eliminate small objects from an image. So, for instance, the three small squares, two of the circles, and most of the noisy uh, or uh, black rectangular areas have been blended into the background of the image. In the note also in this figure B, the pronounced black border. This is a result of padding the border of the original image with zeros and then trimming off the padded areas after filtering. Some of the black was filtered into all filtered images but become truly objectionable for the images smoothed with the larger filters. So next, the general implementation or for filtering an m by n image with a weighted averaging filter of size m cross n is given by the expression g of x comma y is equal to summation s is equal to minus a2 plus a summation t is equal to minus b2 b w of s of t f of x plus s y plus t whole divided by summation s is equal to minus a 2 plus a summation t is equal to minus b2 plus b w of s comma t. So, as mentioned earlier, an important application of spatial filtering, that to spatial averaging, is to blur an image for the purpose of getting a gross representation of objects of interest, such that the intensity of the smaller object blends with the background and the larger objects become blob-like and easy to affect. The size of the mask establishes the relative size of the objects that will be blended with the background. As an illustration, consider this figure, which is an image from the Hubble Space Telescope in orbit around the Earth. So this figure B shows the result of 15 cross 15 averaging mask to this image. We see that a number of objects have either blended with the background or their intensities have diminished considerably when compared to this original image. It is a difficult to follow an operation like this with thresholding. Eliminate. Why we need thresholding? To eliminate the objects based on their intensity. The result of using the thresholding function of this figure B with a threshold value equal to 25% of the highest intensity in the blurred image, as shown in this figure C. Comparing this result with the original image, we see that it is a reasonable representation of what we could consider to the largest, brightest objects in the image. Okay, in this figure, the figure B, it's a original image courtesy of NASA. So let us see. The next topic of our discussion is order statistic filters can also be called as nonlinear filters. Ordering or ranking the pixels contained in the image area encompasses by the filter, then replacing the value of the center pixel with the value of ranking result. So, for this purpose, we are going to use median filter. So, what the median filter will do? Which replaces the value of pixel by the median of intensity values in the neighborhood. Good noise reduction capabilities with less smoothing are the requirements. So example, impulse noise or salt and pepper noise. This figure shows an X-ray image of circuit board heavily corrupted by salt and pepper noise. To illustrate the point about the superiority of the median uh, filtering over average filtering, in situations such as this, we show in this figure B, the result of processing the noisy image with a 3 by 3 neighborhood averaging mask, and in figure C, the result of using 3 by 3 median filter. The averaging filter blurred the image and its noise reduction performance was poor. The superiority in all the aspects or aspects of median filter over the averaging filter in this case is quite evident. In general, median filtering is much better suited than the averaging for the removal of salt pepper noise. So now let us consider the next topic, sharpening spatial filters. So what is the foundation of sharpening spatial filters? The basic definition of first order derivative of a one-dimensional function f of x is given by del f by del x is equal to f of x plus 1 minus f of x. Second derivative is given by del square f divided by del x square is equal to f of x plus 1 plus f of x minus 1 minus 2 f of x. So, to illustrate this and to examine the similarities and differences between the first order and the second order derivatives of a digital function, Consider the example as shown in this particular slide. A figure 3.36. So this is what the figure, this is a figure 4.4. Actually, the center figure B, it's a figure A, the first one. Second one is the figure B. And third one is the figure C. So this center figure B shows a selection of a scan line, that is the intensity profile. The values inside the small square or the intensity values in the scan line, which are plotted as block dots, in the figure A. You can observe here the values in the square as taken as 6, 6, 6, 6. So same thing can be considered as black dots and are represented in this figure A. So this is the value 6, and for this 6, 6, 6, this is 5, 4, 3, 2, 1, 1, 1, 1, 1. Again, we're going to have 6, 6, 6, 6, 6. So these values will be represented as black dots in the figure A. The dashed line, you can see here the dashed lines connecting the black dots is included to aid the visualization. As the figure shows, the scan line contains the intensity ramp. There are three sections of constant intensity. Here, constant intensity is there, constant ramp, intensity step. So you can see here the circles indicate the onset or the end of intensity transitions. The first and the second order derivatives computed using the two preceding definitions are included below the scan line in figure B. You can see here. So this is what the first derivative value. So what the formula says, it's a del, that is the first derivative formula. It starts with like f of x plus 1 minus f of x. So if you're going to consider the this is the f of x, the second place. So f of x 6. So 6 minus 6 is equal to 0. So f of x minus f of x minus 1. So that is what the resultant will be equal to 0. Similarly, if this is the f of x, so 6 minus 6 is equal to 0. And like this, so 5 minus 6 is equal to minus 1. 4 minus 5 is equal to minus 1. So these are resultant of the first derivative. And similarly, the second derivative, what it says, so f of x plus 1 plus f of x minus 1 minus 2 of f of x. So here, if you're going to consider this is f of x, so this place is f of x minus 1 and this is f of x plus 1. Now that means 6 and 6. 6 plus 6, 12 minus 2fx, that is 2 into 6 is equal to 12. So here 12 minus 12 is the 0 is the answer. So in a similar manner, if you're going to consider this as your fx, so this is what your f of x minus 1 and this is what your f of x x plus 1. So these two should be added and subtracted with 2 fx, that is 12. So 12, 11, 12 minus 12 plus 11 is equal to minus 1. So these are the resultant of the second derivative for this figure B. The same thing will be the first derivative and the second derivative are represented on this figure C. So you can see here the black dots will give you the resultants of the first derivative, and this plain square will going to give, small square will going to give the second derivative values, pixel values. You can see here. So this is what the first derivative values. So 0, 0, minus 1. So here you can see here the first derivative value, which are represented using the black dots. So 0, 0. So this is what minus 1, minus 1, minus 1, minus 1, minus 1, right? Then 0, 0, 0. So like this, we're going to get 5 here. The value for this is 5. Next will be that going to follow all 4 zeros. In a similar manner, so we can have the pixels, the resultant after getting the second derivative are represented on this, that can be seen on this figure C by, so that is represented by dashed lines. So values, I told you the plain squares. So we can see here, this is what the value 0. So here 0 is there, 0, and the minus 1, 0, and yeah, 0. So all this will going to give, this is what the plus 1 and 5, right? Sorry, here the 5 is there, minus 5 is there, and all zeros are there. So like this, we can go and represent the values. So our next topic for discussion is using the second derivative for image sharpening. The Laplacian discrete formulation of second order derivative used for the constructing filter mask. Isotropic filters response independent of the direction of the discontinuities in the image to which the filter is applied. So usually rotation invariant. Simplest isotropic derivative operator Laplacian is given by delta square F is equal to del square F divided by del x square plus del square F divided by del y square. Discrete form, that is in the x direction, the formula can be del square F divided by del square is equal to f of x plus 1 comma y plus f of x minus 1 y minus 2f of x comma y. In the y direction, this will be given by del square f divided by del y square is equal to f of x y plus 1 plus f of x comma y minus 1 minus 2f of x comma y. So del square f is equal to f of x plus 1 comma y plus f of x minus 1 y plus f of x comma y plus 1 plus f of x comma y minus 1 minus 4f of x comma y. So this equation can be implemented using this Laplacian masks. So here figure A shows it is isotropic result for rotations in increments of 90 degree. Figure B is an isotropic result for rotation in increments of 45 degree, and C and D are two other implementation of Laplacian found frequently in practice. So both will going to C and D, both will going to give a negative definitions of the second derivative. So unsharp, next topic is unsharp masking and high boost filtering. Blur what are the procedure steps we need to do for unsharp masking and high boost filtering. First, blur the original image f of x comma y. Subtract the blurred image f dash x comma y from the original. G mask of x comma y, that is output, is equal to f of x comma y minus f dash x comma y. G of x comma y is equal to f of x comma y plus k into g mask of x comma y. Then add the mask to the original. K is greater than 1 implies I boost filtering. K is equal to 1 implies unsharp masking. So this figure for implementation of Laplacian. So the first figure is a slightly blurred image of the north pole of the moon. Second, Laplacian without scale. Third is the Laplacian with scaling. Fourth image is a sharpened using the mask. The last image picture is a resultant of using the mask. Now, let us see. So, this particular figure explains how unsharp masking works. The intensity profile is the figure A can be interpreted as horizontal scan line through vertical scan that transition from dark to light region in an image. This figure B shows the result of smoothing superimposed on the original signal shown with respect to the reference lines can be seen here. The figure C, it is unsharp mask obtained by subtracting blurred image or blurred signal from the original image. And you can compare this result with the previous one. So figure C corresponding to the ramp in the figure A, we note that unsharp mask in figure C is very much similar to what we would obtain using the second order derivative. This figure D is the final sharpened result obtained by adding the mask to the original image or the signal. So next topic, using first order derivatives for nonlinear or image sharpening, that is the gradient. Gradient of f at x comma y del f is equal to grade of f is equal to gx gy is equal to del fx del f by del x del f by del y. This vector points in the direction of greatest rate of change of f at location xy. The magnitude of length of grade of f is given by m of x comma y is equal to magnitude of del f is equal to square root of gx square plus 9y square. M of x comma y with x comma y varying overall f is called the gradient image. The gradient is a linear operator but not rotation invariant or isotropic. the magnitude is not linear but is isotropic. So, using first order derivatives for image sharpening, the gradient definitions proposed by Roberts in the year 1965 using cross differences, where g of x is equal to z9 minus z5 and g of x is equal to z8 minus zx. Can observe in this, so here z9 and this is what the z5. So we're going to subtract z5 from z9, and for gx, z8 will be subtracted um, from, zx is subtracted from z8. M of x comma y is equal to z9 minus z5 whole square plus z8 minus zx whole square whole to the power of 1 by 2. M of xy is approximately equal to determinant of z9 minus z5 plus determinant of z8 minus zx. So these are all Robert cross gradient operators. So figure A, it shows a 3 by 3 region of an image where the z's are intensity values. So all z, that is z1, z2, z3 till z9 will represent the intensity values, and B to C, that is Roberts cross gradient operators. After using this, you're going to get the values like -1, 0, 0, 1, 0, -1, 1, 0. So now let us see. Using first order derivatives for nonlinear image sharpening, the gradient approximations to gx and gy using a 3 by 3 neighborhood centered on z5. So gx is equal to del f by del x is equal to z7 plus 2z8 plus z9 minus z1 plus 2z2 plus z3. Gy is equal to del f by del y is equal to z3 plus 2z6 plus z9 minus of z1 plus 2z4 plus z7. M of xy approximately equal to determinant of z7 plus 2z8 plus z9 of minus z1 plus 2z2 plus z3 plus determinant of z3 plus 2z6 plus z9 minus z1 plus 2z4 plus z7. So these are all the Sobel operators. So that means, so a 3 by 3 region of the image. So here also all z's will going to, that is, it's very small. So z1 to z9 will going to give the intensity values. So the B to C Roberts cross gradient operators and D to C Sobel operators, all the mask coefficients sum to 0 as expected of a derivative operator. So this is what the implementation of the equations. So this is a figure A will give you optical image of the contact lens. So it's a actually defects on the boundary at 4 and 5 o'clock. This image has been taken during that time. And the second figure, it's a Sobel gradient, that is original image courtesy of Pete Sites Perceptics Corporation. So now let us end this session 4 with the discussion of multiple choice questions. In neighborhood operations, okay, here is the first question. In neighborhood operation, working is being done with the value of image pixel in the neighborhood and the corresponding value of sub-image that has same dimension as neighborhood. The sub-image is referred as, following are the options. First one filter, second is the mask, and third is the template. Fourth is all of the mentioned. So what is the answer? It's option D, all of the mentioned. That is, the sub-image is referred as filter, mask, and even the template. Okay, so next question. In linear spatial filtering, what is the pixel of the image under mask corresponding to the mask coefficient W of 1 minus 1, assuming a 3 by 3 mask? Option x comma minus y, B f of x plus 1 comma y, C f of x comma y minus 1, D f of x plus 1 comma y minus 1. So answer is D, because the pixel corresponding to mask coefficient 3 by 3 mask. So that is W of 0 comma 0 is f of x comma y, and so for 1 minus 1 it's f of x plus 1 and y of minus 1. So third question, which of the following is or a non-linear operation? So options are computation of variance, computation of median, all of the mentioned, none of the mentioned. Actually, the answer is it's option C. So computation of variance as well as the median comes under, it's under non-linear operation. So we're going to consider both the option. The next question, what is the output of smoothing linear spatial filter? Options are median of pixels, maximum of pixels, minimum of pixels, average of pixels. So it's option D. The output or response of a smoothing linear spatial filter is simply the average of the pixels contained in the neighborhood of the filter marks. So that is what I have explained. So fifth question, which of the following is the disadvantage of using smoothing filter? Options are blur edges, blur inner pixels, remove sharp transitions, and sharp edges. So option A is the correct one. That is what? Blur edges. So edges, which almost always are desirable features of the image, so also are characterized by sharp transitions in the gray level. So averaging filters have an undesirable side effect that they blur these edges. So next question, sixth one. Which of the following comes under the application of image blurring? First one, object detection. Second, gross representation. Third one, object motion. Fourth one, image segmentation. So answer B is the correct one, as an important application of the spatial or averaging is to blur an image for the purpose of getting a gross representation of interested objects, such that the intensity of the small objects blends with the background and large objects become easy to detect. So next question, which of the following filters response is based on ranking of pixels? Is it a non-linear smoothing filters? Is it a linear smoothing filters? sharpening filters or geometric mean filter? Obviously, it's a non-linear smoothing filter. That is what the option A. So, order statistic filters are can be called as what? Non-linear smoothing filters. So, whose response is based on the ordering or the ranking the pixels contained in the image area encompassed by the filter and then replacing the value of the central pixel with the value determined by the ranking result. So, eighth question, which term is used to indicate that pixels are multiplied by different coefficients? First one, weighted average. Second, squared average. Spatial average, none of the mentioned. Its answer A is called the weighted average, since more importance is given to some pixels. So next question, that is what ninth one. Smoothing filter is used for which of the following work? Is it for blurring, for noise reduction, all of the mentioned, none of the mentioned? It's for both blurring as well as noise reduction. So smoothing filters are used for blurring as well as noise reduction. So last question for our discussion is a spatial averaging filter having all the coefficients equal is termed first option a box filter, second a weighted average, third, a standard average filter. Fourth one, a median filter. So answer is, I'll read the question again. A spatial averaging filter having all the coefficients equal is termed as box filter because an averaging filter is termed as a box filter if all the coefficients of the spatial averaging filters are equal. So I'm going to end this session 4 by saying thank you all. Thank you.